Hello. Okay, my mic is officially working. That is awesome. Hmm. But I seem to be having some issues with the stream quality, at least. Um. Okay, so we done these problems. Was it yesterday? And think we even did till here. So we were at valid Sudoku, which looks like a math problem essentially. So basically, check if according to the current numbers that we have, if our Sudoku is a valid Sudoku or not. So basically, all you have to do is um, check if so basically n square for checking each row if it has unique digits. Then same n square for unique columns, and then checking 1, 2, 3, 4, 5, 6, and 9 3 by 3s for unique boxes. So that's what brute force looks like. This is not very highly downvoted, so there might be a better solution as well. Each. Hmm. So to store if you found it in that row or not, or in that column or not, you keep a map of size n, size 9, and then reset that map for every row, and then in the next row for every column. So the space it'll take is sort of 1 for a 9 by 9 Sudoku. And same goes for this. So I think since it's maths, I don't think there's any point looking at the solution. Let's see if there is something different. Yeah, so basically this array stores if this row has this number or not. And when you do find a number on the board, you it's a string, you convert it into a number, then convert it to index range, and then for a box, it belongs to I by 3 times 3. So basically, if it's within something like I percent 3 plus j by 3, 4 becomes 3, um, 5 becomes 3, 6 becomes 3, and 7 becomes, yeah, so basically each box, this is that for each box. So then this is n square. So whatever solution do is going to be n square. Hmm, nice question. So according to yeah, so our question is not really about finding a valid Sudoku as per the description of actual Sudoku, but just satisfying these conditions basically. Okay, it's an if else problem, really not gonna do that. Combination sum. Given a set of candidate numbers without duplicates and a target, find all unique combinations in candidates where candidate numbers sum to target. So basically, find subsets of a set whose sum is a given number. Hmm. Okay, so one okay, so brute force, find all sets, find sum of all sets. While creating those sets, if the sum of the set is target, then you choose that set and put it in an answer. Now that's going to be 2 to the power n, because it's going to be almost 2 to the power n. So because it's going to be nc1, nc2, nc3, nc4. Number of ways of choosing. So you choose one element, that's one subset. You choose any two elements, that's another type of subsets, which is 4c2 for our first example. So nc2, similarly nc3, nc4 till ncn for any n, and the sum of that series is 2 to the power n, except nc0, which is, well, it doesn't matter, that's minus 1 in the end, so it's still 2 to the power n. Um, the same repeated number may be chosen from candidates unlimited number of times. Oh, so okay, so 2 to the power n is a subset of our answer. We can actually use the same number multiple times. So, mm, so number of ways of making a subset of size 1 will be n. Number of ways of making a subset of size 2 will be n square. Number of ways of making subset of size 3 will be n cube. So our only option is hopefully our target's not too big and we finish as soon as possible, like by n or n square or n cube or n4, depending on our size of candidate. So hmm. So yeah, so this is obviously the brute force I was talking about. One solution that does come to mind is backtracking, because it says to choose numbers and then check a condition. That's sort of like from a set, choose of some items in that set, um, such that uh, some condition becomes true. So yeah, so how backtracking would work in something like this is, say, let's start with this entire array. So, and this will always be our array. So your option is to um, pick this or not pick this. So that cuts down our sample space to current sum as say 2, and then the other one would have current sum as 0. Now each of these splits into two categories. One where current sum is 4, basically when you choose 2 again, and one where you don't choose 2, where you choose the next one. So that makes it 5. And then this one splits into 2 as well. Um, so current sum becomes either 3, so you choose 3, or you skip 3 and you choose 6. Then you again break this again. CR is 6, or CR is 4 plus 3, which is 7. Um, or else CR is 5 plus. So we're not going to add 2 here because that will already be taken care of in some other case that happened before this. CR, sorry, and is not choosing 3, uh, not choosing 3 versus choosing 3. So 5 and 3 becomes, sorry, so you, first option is to choose where you are at, so 5 and 3 becomes 8, or becomes 5 and 6 becomes 11. And then for a right side, we don't choose anything again. I think this option will not really be used, not be saved. So what we're just gonna do is current sum will be, oh no, sorry, we will be using this. Um, so that's one, and for now, say it'll again be 0, or you choose the next one, which is 6, or for 3, you choose 3 again, so that is 6, or it'll become 9. So for these, okay, once more we will 2L and 2. So again, either you choose 2 or you choose 3. So it becomes 8 or 9. And for the second one, it becomes, since it's already target, we return. If it's greater than equal, if it's equal to the target, we add our whatever we've used in this list. We add that to our answer. Add, and for all those that it's greater, we'll return in the previous step itself. So left side of the tree is done, and here again we have CR is 0. We're at the last. Um, so now we either do this for CR0 or we add 7. Then for 3 CR6 we either add 3 because we are at that 3 point. So took care of that from sorry, we were at, this was splitting this, the 0. Now this CR6 is from the 0 where it is at 6 right now. So it'll either be 12. So either add CR6 would mean either take this or skip it. I think we didn't take care of the take. Um, I think if it's less, then we then we obviously pick the next one. No, we can still skip it, which is taken care in this part, right? So yeah, so that's fine. So either we got our answer over there or we are on, we picked 6. So we pick 6 again, or we skip 6 and pick 7. So that becomes 19. Sorry, 6 plus 7 is 13. For this case, we are at 3, so either it becomes 9 or we skip that and we pick the next one, so it becomes 12. And for CR9, we either pick 6 again or we pick 7, which makes it 15 or 16. So for these cases, it's greater than 7, we return. For this case, it's not, if it's equal to 7, so we save this. And for this case, our remaining uh, candidates are empty. When that's true, we also return. Okay, so that's the backtracking answer. Now, writing it down in examples was pretty lengthy, but I think coding it out would actually be much, much smaller. So let's just do that. Where was I? Okay, yeah. So we need a list that we'll be returning, which will be our vector int return list. Um, it's passed by reference here. Okay. So see how you get the subset of vector. So I can just I think you can just create another vector from the new with the iterators. Yeah. Okay. Yeah. I think that's the best way. Okay. So let's just call helper on our return value, which we will pass by reference that gets updated. Candidates, um, the target, the current sum. Was there anything else? Current sum, targets. We can also use index so that if you don't want to manipulate the candidates. So let's see what this can do. Void helper. So if you've never written backtracking, you should definitely write it so that you can understand how it works. The more you write backtracking code, the better you'll understand recursion. I have done backtracking a bit, but not a lot. So I would like to practice on that. So that's why I'm writing this down right now. So let's just copy that. Our return value, our vector int candidates, our integer target, and our current sum. Current sum, let's make it current, and the index we're at. So we start with 0, of course. Okay, so if our okay, so we also have to keep track of our current list that we've generated, that we would need to push in our actual result in this list. So uh, path, let's call path. So here we have our path, which will be a vector int path. Now why am I passing this? Why am I passing this? Do I need to pass this? Is the question. Um, do I need to pass a path? Yes, because this is the variable that we'll be using to create more paths, uh, which we can't do in the start because that then will be created at every recursion call. We need an existing path that we start from. If you saw, we started from uh, our uh, blank case where we then added either we added 2 or we added nothing and moved to index 1. So yeah, so this is what we have to pass. Should have kept the example. Um, an example always helps you, see if you're going wrong. If your code itself doesn't set true for, work for your example. So, okay, so if your candidates is empty, your possible candidates, then you just return. Also, if your current sum is equal to target, you add your path, pushback path, and then you return because let's say there are no unique combinations in candidates, whether candidate number some target, same repeat number may be chosen from a number of times. Okay, so to avoid, say if there is 2 and another 2, since we can already use that 2 multiple times, there's no point keeping that 2 in the array itself. So remove duplicates from vector. Is this a good uh, huh? So we unique these, and uh, Now this is already going to be more than n log n, so I guess the best option is to sort it as well. So we'll just sort it because I'm not sure actually. This might be useless as well. Um, but we'll just sort it now and see what the timings come up as without sort. I don't think it's necessary because we're gonna pick every character, every number and its combination nevertheless. Okay. Hmm. Also, if candidate index is greater than target or current plus candidate index is greater than target, which means basically your number that you're gonna choose right now is going to have going to increase the number. Let's skip this for now. Yeah, if the number itself is greater than the target, then you of course don't have to add it. Your previous result will be better because it's already sorted. Okay. Okay. Now to write when the actual, now to create the actual path. So you have two options. One is to select your number. Okay, let's do the one without selecting the number. So that will be helper ret. Your candidates will of course remain the same. Your target will remain the same. Your current will remain the same. And just your index moves. And your path will remain the same because you didn't choose it. Choose the number. Um, then again, this remains the same. Your candidate remains the same. Your target remains the same. Your current, you can change the target actually and check for target 0 here instead of keeping a current, but that's fine. Current is current plus candidates at index, and so either you include the current number. So what we did here was not include the current number and move on to the next one. What we can do is now include the current number and then the same thing. So we don't have to include the number and not include and move on because that will be taken care of by the helper inside this one, which will be just moving forward. So path dot push back. Stream's delayed a lot. Something I can notice. Probably like 5 minutes maybe. Okay. Path dot push back the current value, which is can current, sorry, can index, and it's not going to be can dot size if index is greater than can dot size, because you're not changing can. So we add this to our path and then we use that path. Sorry, we were left with index, right? We don't change the index and that's our new path. Okay, so we've added the case what all we want to return. We've taken care of both cases, including and not including a number, and when to exit. Did I miss something? Um, no matching function. So ret can int 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 path. Ret is this is right. Vector int can is right. Right? Why is that so? Target is int. Current is int. Index is int. Path is int. Sorry, path is vector int. Um, Vector vector star vector and int and. Why is this int and? Anyway. Hmm. Sorry. Let's try putting this here. Then we'll remember if it is in function definition or call. Oh, it should be in definition, right? Okay, so basically heap buffer overflow. Okay, it could be an overflow or an bad access to our candidate. But if a yeah, this looks better, more promising. Memory limit exceeded. Yeah, because we're calling on the stack uh, too much. Okay. We can also, sorry, there's another condition I think that if the current is also greater than the target, I think we didn't check for this, which we should have, of course. We break off. Okay, yeah, so that works. I just want to see if it works without sorting, which it should, according to me. Um, this array is already sorted. Let's unsort this. It definitely works, but I think sorting does actually help. Yeah, see if you sort this. Okay, we'll just not sort it and see and submit. See the time. I'm not even sure this might have just worked for this scenario. 2384. Output was 33222, and what you expected was two, taking two, and then so I think this is actually false. This is not true because what that does is it takes 2, 3 and says even if you're skipping 3, you stop counting altogether. Let me see if they want it sorted. The result should be sorted or not. Submissions. Yeah, okay, great. So it did work, definitely. Let's see if sorting it helps. It definitely should, especially for bigger cases. Okay, that was unexpected, highly unexpected. I think sort is taking some memory as well. Is there any place we can free some memory? Nope. Okay. It's a bad solution, they're saying. So let's not sort it. And let's not take uniques. I mean, this I think just actually makes the answer space shorter. But let's see. 16 ms using pack tracking, easy to understand. Is there a DP solution as well? Okay, so combination sum. Candidates target return value combination and the index. So for each index, you include that, calculate the answer with that included, and then remove it, and then put remove that, and then try it with another index. So I'm pretty sure we've done the same thing, except we've not. I think they have not used the same candidate again and again. Is that true? Uh, I is one, and then they add it to the list, and then they call it with the same I. So they have used it again and again. So wondering. I'm wondering why this solution is taking more time. Is it because it's purely backtracking? Oh, it's already without duplicates, so you don't need to do unique. Um, so they're saying use a for loop inside your backtracking where if you have an index, and then add it and remove it from your list. This I plus 1 is not gonna work. Uh, this. Okay. Well, we'll never know why this is slower than the other one. We might know. Sorting takes time in memory, so you don't have to sort it. But I don't. I think if you provide this solution, I am 100% sure nobody is going to question your knowledge, because this fairly enough the number of times a condition is checked is going to be the very same for these solutions as well as the one that I've just written down. Okay, so let's move on. Combination sum 2. I think we'll just copy this solution for a reference. Sorry, what happened? Maybe I just refresh the page. Yeah, okay, wasn't done refreshing. So we just copy this solution. Uh, Given a collection of candidates and a target, find all unique combinations where each number may be used only once. Cool. So basically, this is the same thing. Uh, Wherein you can only, if you used it, you can use it only again once. So you always have to check for the next number. That is basically. So 116, we do have that. We have 26, we have 17. Oh, 17 is the same as 71. So we can't do unique because just one sec. Yeah, so we need to take care of duplicates. One. Also, I think one of the cases didn't come up. 1, 2, and 5 for some reason. Mm, so it was go ahead and don't use it, or use it and then move ahead. Oh, so okay, so think need to add this here. Um, Now the only problem this case has is of duplicates. Yeah, this is 2, 1, 5, and 1 to 5, and then 1, 7, and 7, 1. So what if we sort it? So it is gonna pick up 1, 1, 6, but then if it picks up 1, 7, it's gonna skip 1 and then pick 1, 7 again. So how do we? Okay, we can try something like this. We can just take the unique of our response. But for that, we would also need to sort our list. Hmm. So we got this, but we could not find the uniques. How are two vectors unique, unless you can define how to use unique. Uh, Unique CPP. If we can give a function predictor, yeah. Let's try doing that. Unique function, and what this will do is now these two are unique if for I equal to 0, I is if a dot size is not equal to b dot size, the sizes are different, they are not, they are directly unique. For I equal to 0, I is less than a dot size I plus plus if a I is not equal to bi, return false, return true, and after everything return true. Okay, don't say int I. Okay, it's in C you might have you might not have to declare this. Sorry, what? Bool invalid use a non-static member function. Let's see. My function, and how's my function declared? It is bool with, okay, so what is it expecting? Unique vector 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 vector. Let's just see the function. Is this the question? Okay. Unique uh what? Uh New end v dot pushback v dot pushback continue string v dot back dot pushback a dot pushback a. This is cout, and they're doing unique on v dot beginning and v dot end. I mean, it is not working is the problem. In red dot end, right? It's not working. So seems like this might not be the solution, especially since this is not working. Be funny if it worked now. Unique vector of vectors, right? Oh, they're saying it should be sorted. So, sorry. So let's see if we just sort it, if that helps. Pretty slow. What? What is this? What is this? Nice. Okay, I guess this might not be the solution. So let's see where we went wrong. Okay. If what is this order variable? The second variable, okay. So if I exists and the and num I is equal. So I think this might be sorted then. Your Yeah, this is sorted. So now if two numbers are the same and I is greater than order, which means this is not the first time. So you're just skipping duplicates. I don't think that makes sense. I mean, to me, it's not making a lot of sense. I think we saw the solution somewhere over here. Um, if basically beginning is where your current index is. Now, if anybody would like to pitch in, be my guest. But what's not making sense is if I is 0, so basically, if you're starting a new sequence and ah, so if you're starting a new sequence and it's a question. Yeah, so if you're starting a new sequence and your current number is same as the start of the previous sequence, then like if you're not starting a sequence, uh, if you're starting a sequence, you can go ahead normally. But if you're not starting a sequence and you use, say you're not starting a sequence and uh, these numbers are different, then you can continue. But if you're not starting a sequence and the two numbers are the same, if you're not at the start of the sequence and the two numbers are the same, what that would do is two numbers are, if the two numbers are same, so you say you have 1, 2, 2, and you're at the second 2. Now, does it say in the solution that it's going to be all unique? No, because it can have 1, 2, 2, right? So, so say you're at 1, 2, 2, um, and the target is say 6 or something. So if you're at 1, 2, 2, if I, if the start of this set, no, not this set. Hmm. If you're not at the start of the set and your two numbers match, then you don't. So what this is saying is start at each index, and for each such sequence, include the current value. For each such sequence, include the current value. So include 1, starting from 1, and you include 2 as well, then 3 and 4 and so on. When you start at the next one, oh, sorry, so no, this actually is, the first loop is checking each candidate individually. Then inside the first recursion, when the first candidate is being checked individually, you start with the second candidate with it. If the current sum is already the target, then you quit. Otherwise, you push every element apart from your the element that you already have in it and check. And for each those, you push every other element after it, and so on and so forth. So basically, we're making all the possible answers, and except when we just exceed our answer. That's when we're quitting. But with the condition here is that if I is the beginning, that no matter what your set is, you might already have set, but if you are if you are if you're adding a number to the set for the first time in this loop, then you may add it. So our case of 117, say we're at the loop where we're the first one. We've skipped the second one and we're at 7, so we add 1 and 7. Um, so then say we have skipped ones in the first main loop. We've skipped 1, we've skipped 2. Sorry, we skipped 1, and then we come at the second one where I is going to be 2. Now since I is 2, if the first if fails, now this number is the same as the previous number, so the second if also fails. Because if it is not same as the previous number, uh, so if it's the same as the previous number would have already taken care of all the cases of having this of uh, of not including this number. So this is only checked if this is not the first number in the iteration, uh, say the second number in the iteration. Sorry, not the second. Say any but the first number, because only in that case your previous number would be included, and he would have taken care of all the cases. So let's see if we can implement that in just our solution without the fors. So what it's saying is that no, we can't, I guess, because what we are only sending is where to start from now, not where how many. So based on how many elements our path has, you can check that. So if I equals to beginning means, so if path dot size is either 0, which means no elements are included, or if it's not 0, then candidate I is not equal to candidate of I minus 1. Okay, so this is some condition I was not able to come up with. It says if the path is say empty, then obviously we can include our element because it's not going to create any duplicates. But if the path is not empty, we check if the element that we're trying to include has already been included. So if it already has been included, he will already be taking care of all the cases that this element was going to. So we're reducing our test case, our total search space. Um, Hence time, and also obviously implementing the correct logic. So output did not include 1 1. So why is that? So we get we have 1 included. Oh, how was it taking care of the part where 1 1 was to be selected? So you took 1 and then started with 1. Sorry. If it's the start of what? But say if one's already been pushed in, then also it's if it's the start. So it's basically if it's the first element, if it's the, so say if path has something, if path has something and index is 1, which means, sorry, I is begin, which means none of the remaining candidates, have been added to this path. Uh, and path dot size is not path dot size really. So basically, say if you were at the third index, you have nothing included yet, and you're going to be beginning at the fourth index, but so what the for loop doing is checking for candidates is, say, it goes at each index of the candidates and then selects it, and then inside that it goes to each index and selects it. So it's okay to select, so it's okay to make a path from that index if i's begin. So is I begin if path has something? Yes, it can be. When is it going to be the case? So when index is 2, let's say there's 1, 2, and 3, and 4. So 1, let's say for 2, we have the case, right now say I is 1 here, I is beginning. Let's say we did not include anything yet. Sorry, for the first case, uh, I starts at 0, then I becomes 1. For the case where we have 1 and 2 selected, sorry, 1, 2 is gonna get selected at I1. And when we take only 2, I is 0 and we have nothing selected till now. Then you take I is 3, sorry, I is 1 for 2 getting selected. Then we have I is 3, sorry, I is 2 for our main outside loop. When 3 gets selected, when 3 gets selected, I is 2 and 3 gets selected solely, and then the path is 3, I is 2. So say now you're selecting the next one. For this case, I will be 0, 1, 2, 3. I will always obviously be the index of the number you are adding. And how do you compare that to beginning? Beginning is if you are adding, if you are pushing to your current path for the first time. So if size of path is, no, because when you pushed 1, it comes back. So if you're pushing to your current path for the first time, but I am not having any current paths. I'm having, like, all my paths are current paths. I'm not having any included or non-included areas. Um, so, oh, okay. So my case is this, I think, is actually this is the case where I'm not including the current, where I am not including the current item and just moving on. And this is where I am including the current item. So if I'm not including, the current item, so their cases are different. So they run a little differently. They are say 1, 1, 2, 3, 4. So first they take 1 out, and then they make 1, and then we have an option of selecting 1, 2, 3, 4, and then they make 1, 1. Then they have the option of selecting 2, 3, 4. So they do 1, 1, 2. Whereas what I am doing is I go 1, 1, 2, 3, 4. So I do 1, 2, 3, 4, 1, 1, 2, 3, 4, and then I do 1, 1, sorry, 1, you come out and you 1, 1. Then when you have left 2, 3, 4, so I don't use any. So I get 1, 1. Then I get 1, 1, 2. Wait. Then Then I get 1, 1, 3. Then I get 1, 1, 4. I'm getting the same, but I'm getting 1, 2, 3, 4 first, I think. So it was select one, then recursion, select this, recursion, select this, recursion, select the recursion, select this. Then you come out of this. Selected this, and then you push back. Then you don't select this. Oh, so I get 1, then I get 1, 4, I get 1, 3, 1, 2, 1, 1. Yes, I'm not able to find out what will be the condition in this case without, the fors. Hmm. Let's see if someone has a non-for solution. Hmm. So I is greater than position, which means for the existing path, so you have 1. So when you are checking, so this doesn't require any ifs, I guess. But when you are checking for this one, or maybe, nah, I don't think it's gonna be possible without that. So basically what we're saying is if it's 1, and then if it is uh if path so you can do 1 1, but will you do 1 1 3 when it's 1 on 3? So your if the last element in your path, if your last element in your, not in your path, if your path is empty, nope, you can't check path. Yeah, if your path is empty, no, can't check path because it may or may not have numbers. So you can't use if you do 2 1 1 2 1 3 and 2 1 3, it's going to be duplicate. So it cannot be based on path. But if the number that you're adding is the same as the previous number, but but it is not the last number in the path. So if candidate index, if index is greater than 0 and current index, candidate index is equal to candidate at index minus 1, and the last number in your path is not equal to your current candidate, sorry, is, which means the previous number would have already taken care of this, so you just return over here. Sorry. Try this logic for 2113 test case. Sorry, what pointer index expression base overflowed. You can do it afterwards, maybe. Can't really do it afterwards. You can just do this instead. So basically, what? I haven't changed anything, I'm guessing. How is this getting out of hand? Oh, okay. Stop. Um, and path dot size is greater than 0. Sorry, I can just code. So if they are the same, then that's no problem. But if previous are the last two elements are the same, it doesn't depend on the path size, like I said before. So it doesn't depend on the path size like this. Uh, so if path size is greater than 0 and etc, you return. But if path size is not 0, but if path size is 0, but if path dot size is 0, oh no, sorry. If path size is 0, uh, and if path size is 0, return. If path size is 0 and they're same. I think this is the condition that was earlier. And if they're not the same, but sorry. One sec. So basically what's happening is for one, when it's 1, 1, 2, since 1 is equal to 1 and 2 and we've not selected anything, it's just returning. But what we actually need to do is, since our code is going to stop running for, it's not going to select 2 and 3 and 4 also, we do need to use that. So we don't need to return in case our candidates are not used. Just don't include that. Just don't use. Huh. Just, this might not be foolproof. Yeah. One to do, one to do. How did this happen? Oh, okay. Hmm. Hmm. Well, this might also not be covering all cases. Screw it. I guess we need to learn how to do this instead of doing it this way. So essentially, so what we do in do what we do in backtracking in this way is select an element or not. I mean, not select an element and move forward, or select an element and move forward. And the first case that comes to be is not selecting all the elements. Then, as we retrace back to not selecting the last element, we select one element from the end and try and make a path with that. So our selecting order is actually for 1, 2, 1, 1, 2, 3, 4. We are selecting 4, then 3, then 3, 4, then 2, then 2, 4, then 2, 3, then 2, 3, 4, and so on. In the reverse order basically. But what the for loop does is, so it goes 1, 1, 2, 3, 4. So uh, it starts with 1 and then selects. Let me show you. Yeah. Uh, it selects 1, um, then checks all the condition for 1. Then it selects 1, 1, then checks the condition. Then selects 1, 1, 2, 1, 1, 3, 1, 4. Sorry, 1, 1, 2, 3, 4. Then comes out. Then it selects 1, 1, 2, 3, and one sec. Hello? Yeah, so essentially what it does is, yeah, so 1, 1, 2, 3, 4, then it goes 1, 1, 2, 3, and then stops. 1, 1, 2, 3, and then the index basically goes out.